Hello and welcome to this webinar presented by Evotech CAE and MSC Software, focused on MSC Apex Iberian Lynx, a recent release, and we're looking specifically today at shipbuilding and analysis for large fabricated structures and everything associated with those industries. My name is Steph Evans. I'm the lead FEA engineer with Evotech CAE. Based in the UK, we are technical resellers, elite partners with MSC Software, supporting their full software portfolio, but with our main focus is on consultancy, training and reselling of the MSC Apex CAE platform. So let's get started. Apex for the shipbuilding industry and large fabricated structure industries allows you to achieve massive reductions in model turnaround time based on a number of key technologies, patented technologies, direct modeling focus, CA build and generative model behavior. The user experience is enjoyable, easy to use, easy to learn platform. Many clients and users liken it to a video game, which is completely different to many legacy tool sets where the user interface can often be opaque, difficult to learn and very slow in developing models. It opens up the analysis process to non-specialists, so similar to the user experience, the fact that it's enjoyable. Junior engineers and non-FEA specialists can become productive with Apex very quickly and become very useful in terms of the model build and analysis process. There's flexible license access through the MSC One licensing system, where licenses can be floated across a local or a global network, also giving access to other MSC technologies such as MSC Nostrum, Mark and the Adams multi-body dynamics tool. There are many patented technologies in Apex and a rich suite of scripting, customization, automation technology available through the flexible architecture. These capabilities are very prevalent in the model build, analysis and general FEA requirement across shipbuilding and the large fabricated structure industries, hence the importance that robust FEA has within this development process. That said, Apex gives you the design freedom to develop your current and future products in a manner you have never seen before, mainly focused on the power of Apex coupled with the massive efficiency gains that you can get. So the Apex journey so far, Apex, the original releases were based on CAD to mesh, so easy to use, faster to build models and faster update models. Then with subsequent releases we moved into the ability to go from CAD to results by relying on the embedded Apex structures solver technology, which allowed us to go round the design iteration loop to build and analyze your products quicker. Then with later releases we saw the introduction of the Python application program interface, the API, which means that Apex is now fully controlled and customizable through that Python automation. A subtle change in the messaging or push for Apex has been to change the paradigm from the embedded Apex structures solver to the MSC Nostrum external solution by the Apex Nostrum gateway. A number of interoperability enhancements are all enabled through the MSC Apex Iberian Lynx release. So workflow maturity, so legacy approaches, looking at other tool sets, so Patron or third-party tool sets for both pre and post processing wrapped around the MSC Nostrum process. As Apex came along, it was originally used as a companion tool to allow Apex to build models in a partial sense for then import into Patron or third-party tool for continuing post-processing, then Nostrum, then external support, post-processing support. As Apex has evolved, it's now, or has been, a fully defined pre-processor, but still relying on Patron or third-party tool to do post-processing. But now with Iberian Lynx we have the concept of Apex for Nostrum, where we can build and explore our results post-process Nostrum all in a single wrapper environment without the need for anything else. So functionality growth, original companion tool, we had some level of keyword support which has grown in subsequent releases. We've had Apex as a companion tool where we can set up the jobs and solution types for external Nostrum post-processing. The advent of Apex Iberian Lynx has meant that we are now fully supporting results exploration, so we can post-process Nostrum result files and result data in a single Apex environment. We've also got the ability to deal with orphan mesh, which means we can now take legacy Nostrum bulk data files, read them into Apex, manipulate and modify them without the need to rebuild from the original geometry. And as Apex develops into the future, with a couple of service packs and another significant release planned over 2019, we've got a lot of technology that's coming in which will further improve these functionalities. So how can Apex improve your productivity? Key thing now is that Apex is implicit within your MSC Nostrum workflow, so you don't need to rely on anything else in terms of your model build for the bulk of your FEA development process. It can become your main CA workhorse. Apex is undergoing continual development in terms of model build, analysis and result exploration with every release. The Python-based automation, it now supports build, but also analysis and result exploration, which is new to Iberian Lynx, and we've also got the ability to customize the graphical user interface through a user-defined tool, enabling the user to develop and access their own form and graphical user customization. Apex's current and future development is driven by a desire to address the key industry pains that we see with the contemporary development environments, allowing you to experience the full benefit of an Apex-focused workflow. So let's get started with a couple of examples of some shipbuilding and large fabricated structure analysis, some build types. So let's get started. So looking at Apex automation, so we've got an example here where Apex has been automated with CAD integration. So the Intergraph Smart 3D tool, the geometry CAD tool, is now fully built into Apex with a Python automation. So we can now read in geometry via a Python script. We can develop our shell and beam properties from a neutral XML CAD file direct out of Smart 3D, which means we can build geometry, assemble that model within the Apex environment, and then run our analysis for subsequent linear static and buckling analysis. So the movie playing on the left hand side, we can see how the geometry is read in and manipulated. So we've got 2D shell elements and 1D bar elements that represent the bulk of that global type ship structure. A very complex model build that can be automated very easily to give us the output that we need. So just looking at a couple of shell and bar response in terms of that definition. So the Apex Nostrum workflow. So Apex is fundamental in terms of your Nostrum based workflow with enhanced keyword support for both model import and export, and also at the other end, the post-processing end, we've now got HDF5 result interrogation to take advantage of the powerful results exploration within the Apex environment. We've got multiple keywords supported now. The infographic on the left hand side shows how the number of supported keywords for coordinate frames, multiple constraints, materials properties, model definition and loads of boundary conditions has increased from one of the early releases, Diamond Python, through to the contemporary Apex release, Iberian Lynx. And then the word cloud on the right hand side just shows some of the keywords that are supported, just to give you a flavour of the breadth of support that Apex now has. So in terms of the Apex Nostrum workflow, so again we've got a complex model that's been brought in from the Intergraph environment in this example. So the 3D geometry has been broken down into 2D surfaces and 1D bar elements, or 1D curves to support 1D bar elements, and we can look at specific zones within that model just to give an idea of the complexity, and Apex can handle the model build and assembly connection within that environment. So we've just broken out in a portion of the ship hull. This demonstrates a typical global workflow whereby we build a model, we create analysis scenario, and then we can export that model out to the Nostrum solver, an external Nostrum solver, so we can take advantage of maybe a high performance computing environment where we don't want to solve on our local machine, or we've got some requirement to run MSC Nostrum from a certification perspective. So we can run the job externally, obviously sped up in this case, well, a fairly small model anyway, read the results back in, and then we can post-process using the standard MSC Nostrum, standard Apex result exploration tools. So just bring those results in, and we can see a deformation and a stress plot, both in terms of the shell stresses, but also the 1D environment stresses as well. So yeah, just switching from 2D to 1D stress for the combined axial and bending stress, showing the 1D display, and those are the equivalent stresses developed across those stiffeners. So moving on to a detailed modelling workflow. So we're going to look at zone modelling of the detailed ship hull, but we're going to break out, again using the orphan mesh workflow, coupled with an external MSC Nostrum analysis. We're going to build a local weld zone, which is then grafted into the global FEA model, but gives us the local hotspot stress distribution to support the weld types as we see them. So we've got a number of connection techniques to connect dissimilar mesh regions. These consist of edge tie, glue and discrete ties, potentially with the aid of the Python automation toolset that we've mentioned. This is a powerful technique to hone the analysis, so you could run the global model, look for hotspots, and then using the direct modelling CAE capability and the generative model build within Apex, we can further refine the joint area detail to give us the converged stress response that we would need at that level. So we've brought in this orphan mesh, so we've got no geometry in the model at this level, and we break out a region of the substructure and the plates which support the substructure, and we've used the orphan mesh tool sets, and we'll cover that later on in the webinar, but just to give an overall view of this, we've used the orphan mesh controls to generate the local detail and the local weld regions. We've got chamfers defined at the weld throat, and then we can graft that back into the global model, again using a glue definition at this stage, and then we can run the Nostrum solver, or use the embedded Apex solver to run the process and then read the results back in. So a similar global response to what we looked at previously, but then of course we can zoom in on the local region and run those results and see the hotspots specifically at those weld interfaces for our weld fatigue analysis or anything else we might want to perform from a downstream perspective. So that said, we've now got multiple ways of dealing with hybrid structures. So large fabricated structures can often have hundreds if not thousands of components within a assembly architecture. So Apex can deal with those external CAD import processes and respect within the model browser tree the assembly, sub-assembly and part definition, respecting the original part IDs. So if you've got a true read across in terms of parts list or bill of materials across into the Apex environment, which means it's very efficient in supporting model generation, but also querying and showing different aspects of the model to tie back to the CAD design phase. We've got multiple element types and idealizations within Apex, so 1D, 2D, 3D meshes which can all be tied together to give us discrete component and assembly level FEA generation. The Apex embedded structures solver, or embedded solver, is very useful in terms of verifying discrete parts, sub-assemblies and even full assembly behavior, maybe before we apply our real load cases or before we export to external Nostrum solution for that analysis. So again, we've got multiple connection types such as glue, discrete ties and or joints. So discrete ties and joints are new for the Apex Iberian Lynx release, and we'll look at those in a bit more detail later on. Ultimately, many of these modelling and analysis techniques can offer huge efficiency gains over legacy CAE toolsets. So we're just going to take a quick walk through for this large fabricated structure, this crane assembly. So we've read the geometry in, and we can see in the model browser tree how the model architecture is defined. So we've got a sub-assembly that covers what we're calling the basket, where the operator might work on this structure. We can just highlight a local sub-assembly and just show that in the viewport, and then we can use some of the standard CAD mesh tools within the Apex environment to break that assembly down into the underlying mesh definition or FEA representation, show the 3D equivalent thickness, and then we're going to use the Apex Structures embedded solver just to run a quick verification analysis, typically based around normal modes, a free normal modes analysis, just to show how the structure is tied together. And we can just run that through very quickly, given the size of this model, and understand how the structure will deform, what those mode shapes look like, where the strain energy hotspots would be, and just to understand whether that model is behaving as we would have anticipated. And again, because this is embedded within the Apex environment, we're not into an import-export routine to access those results, and we've got full control over licensing and what have you as well. So just a very quick snapshot of how that structure is going to behave. So once we've got that subassembly verified, we can now look at the larger subassembly, for example. So here we're looking at the basket in its entirety, so just hiding the showing all of that structure and then hiding the geometry and showing all mesh types. So we've got 1D, 2D and 3D elements here, all grafted together using glue and or discrete ties, and then looking at the larger model build. So we've got a number of different idealizations to represent different parts of the structure. So depending on when our hotspot might be or a region of interest, we may choose our mesh fidelity in a given way. So here we're looking at the arm shown in as the pink region, how the stresses would develop in that. So again, 1D, 2D, we've got a transition from a 2D coarse to fine definition here, which we're going to glue together. We've got one of the booms shown as shells and the other one defined as a one-dimensional beam element. So if we turn the beam section display off, we can see that 1D beam element. We've got a joint definition that represents a slide between those two entities. We've got a couple of other sliding and revolute joint definitions that can be used for our mastered load transfer across these interfaces. We've got glued contact here between 2D shells and 3D solids. Again, very quick means of bringing those entity types together. And then we can run our analysis, look in post-processing and hotspot our peak stresses. So we can see here we've got peak stress developed at this weld interface for this fabricated structure. We could hone in that analysis if necessary, looking at some of the 1D stresses which are shown as a three-dimensional display across the section for combined axial and bending stress, and then we can hotspot those 1D entities. We can see that we've got a 1D bar representing a rod structure or cylinder type structure where we've got some local hotspots, and that just concludes the hybrid modelling. So we've got multiple techniques for how we can work with that within an Apex environment. Solver capabilities. So the Apex MSC Nostrum workflow supports linear static, non-modes and linear buckling. This is an example of a typical workflow, given that we've now got the embedded Apex structure solver and the ability to work with externally solved Nostrum information. So we could build a model within the Apex modeler environment. We could then incrementally verify the model, especially for large assemblies with multiple parts, using the internal or embedded solver using the Apex Structures license. Then once verified, we can export the model as a PDF file to an external MSC Nostrum run to develop our production ready results, and then post-process those MSC Nostrum results again using the Apex modeler environment. So full control over the model build, verification, analysis and post-processing. Some of the discrete enhancements that we've seen within this Iberian Lynx release, we've got a number of geometry enhancements. So we've seen this certainly in terms of lofting, but we've now got more mature, more evolved CAD type tools such as revolve, extrude, sweep and lofting, which comes in very handy. So looking at this quick example, which is simple jet engine cowling. So we're going to look at revolving the curve at the front that we've just highlighted, and then spin that around an axis. So we're taking advantage of the Apex magic markers, which effectively allows us to pick things like endpoints and arc centers on the fly. Use the rotation axes. We've got full control in a manual sense, and we can see a preview of that surface. And then middle mouse button to accept, and we've got the front of the engine cowling revolved around to give us the surface on screen. So we've got the front of the structure built. So we're now going to look at lofting a surface, so picking a series of non-connected curves and then building a surface that passes through those curves in a spline sense. We've got full control over edge continuity and what have you, edge tangency, to give us the structure that we want. Geometry from mesh, or the faceted surface creation, which we've looked at with a simple example. So we've read in a bulk data file. We've got no geometry. We can check the shell thicknesses and look at the topology. And what we're going to do here is modify the bulk data file to give us a solid mesh region. So conventional tools would be quite difficult. So what we're going to do is break out the shells in the region where we're going to replace them with 3D elements. Take the CAD out so we can see a hole in that mesh topology. So once we have the mesh that we want to work with, we're now going to create faceted surfaces from that mesh. So pick the mesh, middle mouse button to accept using the defaults in this case. It's built a whole bunch of surfaces created from those original shell elements. Of course, this could be done in automation sense. We've got flat surfaces, but would work equally for curved surfaces. We've remeshed the structure using a new element edge length, and we've got full control now with this faceted surface geometry if we wanted to generate further modifications, so we could seed that surface if necessary. Key here is the faceted surfaces remembered the underlying shell thicknesses, so we don't need to repropertize. That's taken care of. So we dropped in a portion of 3D mesh geometry. We can glue those components together using the standard glue connector technology, and then run the model. So a very quick way to work with orphan bulk data file definition and to modify that to modify or introduce new geometry as required. So some of the Iberian Lynx meshing enhancements. So we've got the concept of mesh diagnosis or meshability introduced in this level or this release. So if you look at a quick example of a tube interface, the tube bracket, so we can 2D mesh that, or 2.5D mesh, hex mesh that, but some of the element quality isn't that great. So we're going to look at surface meshing these faces to drive the underlying hex mesher in the regions shown. Different mesh across a different region. Now we can now see the fillet regions turned yellow, which means we're not able to mesh that. So we can use the diagnose meshability tool and see we've actually got a mismatch in the edge seeding in this region. So we can just match those seeds up, and the solid turns green again, which means it's hex meshable. We can hex mesh the whole thing, and we can do a quick check on the quality. So we've got a very good quality hex mesh defined very quickly using that mesh diagnosis tool within hex meshing. We can look at edge tie enhancements. So again, we're looking at this jet engine cowling. So we might have some internal stiffeners, which are in a separate part sub-assembly within the Apex framework or model database, and we can see that we don't have mesh congruency at those interfaces. Still maintaining the unique part definition. So rather than merging all these into one part, we're keeping them separate. But obviously we need to use the concept of the edge tie to tie these discrete regions together. We can do that. Just wait for the mesh ties, and then now the meshes are tied together between those discrete parts within the sub-assembly or assembly architecture. We look at the edge tie on its own. So for Iberian Lynx, the big change here is that we can now mirror, transform, modify those edge ties as a function of the total model. So we're just going to rotate that model round, or mirror that model round, and then look at the resultant edge ties that are generated. So it's mirrored the edge ties as well. So we've got full mesh control at that level, and then we can run analysis for the fully tied model just to show the local behaviour. Incremental surface meshing, and then some of the shell orientation modifications that have been introduced. So we can look at in this quick example, so we've got 4 holes in the surface. One of the holes is very close to one of the edges, so the standard feature mesh definition has not been defined for the hole near the edge. So using the incremental surface mesher, it will mesh the features as it sees them. Here it's found the hole, it's shown it in red, it says we can't fit that washer in, so we can change the washer width, so just decreasing that for that single region, and then remeshing the whole structure, and those features are preserved within the full mesh definition. We've got the ring of elements as required. One thing which is very important in an aerospace environment, especially if there's going to be downstream hand calcs, is to ensure element alignment for a given region. So we've got shell elements here with the x-axis originally pointing parallel with the long edge. We're changing those now so they're all pointing parallel with the shorter edge, so just a simple rotation of those element XY orientations to make sure we've got element consistency or result consistency in those XY directions. Nostrum Interop Enhancements, so we've got ID management, the ability to renumber entities, coordinate system definition. We've got discrete ties now fully supported, so that's RB2s and 3s. So we can look at this quick example. So we've got, again, this tube into a bracket scenario. We've got the hex mesh as shown, and then we've got a bar element representing the tube with its equivalent section shown now. We can use the renumbering, so we're going to renumber the nodes and elements for the hex mesh region, or the hex mesh part within the assembly. Accept the defaults there, and then we look at the exported bulk data file and look at the element and grid IDs, and they're shown in the 10,000 series as defined. We can create coordinate frames explicitly, so we're creating a cylindrical coordinate frame at the parallel with the axis of this tube and defined at the central point of the tube. Once we've got those coordinate frames defined, we can renumber if we wanted to. We can apply loads or boundary conditions. So here we're constraining the internal faces of the tube in the radial system, or the radial direction of the cylindrical coordinate system. So just picking out the faces. Again, very quick to do that with an Apex environment. Middle mouse button to accept, and we've now got that boundary condition defined. We can use a discrete tie, so we've got rigid RB2 or compliant RB3. So pick the faces of the geometry, and then pick the center point of the bar element, or the endpoint of the bar element. It creates those ties explicitly. And again, this is generative, so if you just change any dimension within the model, the mesh and those tie and even those coordinate frame definitions will get updated. So we can post-process in that local system. So just changed to an externally defined coordinate system, and then we can look at the R, theta and Z displacements. Vectors are shown on screen now, and we've got full control of that coordinate frame definition. We've got the concept of joints within Apex Iberian Lynx. So rather than building manually coordinate frames, local grids within particular coordinate systems, and then tying all those together with RBE2 or 3 elements, we've now got the concept of joint, which effectively does all of that type of build and connection within a single Apex environment, or a single Apex function. So here we're building an involute joint, which is effectively allowing rotation about the axis of connection and connecting the shell structure into the local bar structure. And again, those entities are developed in the model browser to see the specifics, or to modify the specific as necessary. If we look at the resultant BDF file that's written out, we can see the local grids, coordinate frames and connectivity that's defined, and obviously the Apex solver gives us that response as required. We've got result exploration, so we've got the ability to import Nostrum HDF5 result files to probe those results using 0D and 1D probes to develop scalar vector or tensor plots at particular locations, or even over a path, a curve drawn on a model or mesh. And then finally, within this Iberian Lynx release, we've now got the ability to write out those results to an external CSV format, and we can just look at this this structure to show how we could export the bulk data file. We can look at the bulk data file that's created. We can do this on a single file or include file definition. We can run the Nostrum result or generate the Nostrum results externally, and then read that HDF5 file back into the Apex environment. Just bringing that in, importing the results, and the results are brought in successfully. We can now post-process. So we're going to look at a quick animation of displacement, and then we can look at discrete results. So in this case, we're looking at the beam element section outputs based on the combined axial and bending stress, and then we can look at using the 0D cursor, so we can pull out discrete results. And again, this is very visual, so you can, very difficult to make mistakes when you can see the output explicitly. We can generate a table of those probe results and modify the table if we need to, and then write that data out to a CSV file for external post-processing if we need to. Some of the Iberian Lynx customization and automation enhancements. So we've now included scripting support for both analysis and result exploration. Previously we only had it for model build, but now we can effectively black box the whole process by including analysis and result exploration. We've got the ability to custom develop or custom define tools within the Apex environment, as we've seen with one of the earlier examples looking at fastener build. We're just going to look at this quickly. So here we've got a simple example, a simple macro which defines the geometry of a buckling panel under compression. So we can run that script, and we're handling the model build, so mesh, geometry, mesh, properties, loads of boundary conditions, but we're also invoking the Apex solver and result exploration through that automated approach as well. So we get all the way through from a single click of a run script button to having results in the environment with no manual input whatsoever. So this opens Apex up to parametric studies and or the ability for less experienced engineers to take advantage of the full FEA model and analysis capability. So we're just looking at some of the buckling modes here, and we can see we've got a low buckling mode shown in red in the table on the right hand side, and if we wanted to we could rerun the analysis to look at different design setups. So second scripting example here. This one introduces the concept of the custom tool environment. So we've got an Apex strip set up, and the custom tool is set up to read that in via the graphical user interface. So we've got a family of parts here, so we could effectively define this based on all sorts of different dimension and model criteria. But once we've got the inputs that we're happy with, we just press the green button to accept the inputs, and then the model runs, or the macro runs and builds the model. So we've got a sort of flexible tube arrangement here. So building the geometry, so sketch and then revolve that round, mesh the structure, and then we've built the model completely. And then we could have in fact included the analysis and result exploration within this script, but we can see the model response based on those initial parameters. So once we've got this defined, we can we've got full control of the model. The key thing here to say is that Apex really now is a game changer. There's multiple technologies in the Apex environment, which mean we've got a model build, solve, analysis, solve and post-processing capability unseen of before in terms of legacy tool sets, and really now it's open to you to use and to take full advantage of that technology.